Okay. So, and the starting point to define the total energy or total mass of the system will be the definition of the total energy of the Newtonian theory. So I'm trying to do something that probably you have seen when you just derived the Einstein equation. So you start from something that is in the Newtonian theory, you generalize to something which is generally covariant, and then you check, you try to recover the correct limit, the correct Newtonian formula in the limit. And in this particular case, I want to use this notion of mass, where here phi is just the gravitational potential, Newtonian gravitational potential. Which means that in the vacuum is satisfying the Laplace equation. So of course, here in general you have a term with sources, but I'm looking at the equation that is satisfying outside of sources. And then what is the gradient of the gravitational potential? Is just the force that one has to use to hold a unit mass fixed in one position. So essentially here I want to evaluate the mass which is contained inside the surface S. That say to fix the ideas we can consider it as being a sphere. I have a certain distribution of mass inside, and I'm considering a sphere of a certain radius such that the radius is bigger than the distribution of mass. So the distribution of mass is not touching the surface of the sphere. And I'm putting a series of unit mass along the surface of the sphere. The unit mass are attracted gravitationally towards the center. So to keep them fixed at the surface of the sphere, I have to use a certain force. And if you wish, this is a gravitational version of just the Gauss law. It's exactly the same thing that you will see in electromagnetism, where in electromagnetism you can evaluate the charge, total charge contained in a certain surface, just by integrating the flux of electric field around this surface. Here, instead of talking directly about the flux of the gravitational potential, so of a gravitational field, I'm taking also this specification of talking about unit mass that are held fixed in a given position. So, and we can also verify that the formula that I gave makes sense. So either you are already convinced, or if you are not, we can check it in a simple example, just to verify if it makes sense. And the simplest example that we can consider is the one in which I look at the gravitational potential that is created by a point particle. So in this case, the gravitational potential is just minus gm over r. So if you take the gradient of this, you find the usual gravitational force, Newton's law. And then in this particular case, if I compute this integral over s of this quantity d phi, and by the way, n, please interrupt me, there is something that is I forgot to define, or something like that. Is just the unit normal, the outward unit normal with respect to the sphere. Okay, so this n, capital N or small n will always have unit vector normal to the surfaces that I'm considering. So of course, since I want to define global quantities, I will integrate a lot over certain surfaces. But if my notation is not coherent or there is something that is not clear, do not hesitate to interrupt me, to ask. And in this particular case, then the gradient of this object is just in the radial direction. So suppose that I take a sphere with a certain radius. So since this is along the radial direction, I can just compute the gradient and then integrate over a sphere. And so here I just have the volume element of integration over a sphere that contains an r square. R square drops out. And then I can perform the integral over the angles, and I just get a 4 pi. So at least in this particular case, we agree. So the 4 pi, you understand in this way why I put this 4 pi in front of expression. So it's just the 4 pi that I gain when I integrate over the sphere. And at least in this particular example, I recover the mass of the contained inside the sphere there. Okay, so yes, and yeah, and here the sign is also due to the fact because this is the force that I really need to keep there, because the gravitational force, or if you wish, the acceleration induced by the gravitational potential comes with a minus sign. Okay. Okay, so for the moment, I haven't profited from the fact that I really have a static solution, but now I will try to do it. So as I've written, static solution means that I have a killing vector, and now, and I also normalize this killing vector in such a way that xi mu, I define this quantity, and I want that at infinity this quantity tend to 1. And in this context, a static observer is simply an observer whose for velocity is aligned with the killing vector, with the time-like killing vector. In which sense it is static? In the sense that if I have a killing vector here, I can always foliate space-time in such a way that I have this time-like vector, and I have space-like surfaces that are orthogonal to this time-like vector, and essentially an observer whose for velocity is proportional to xi mu has variations that are spatial variations in this coordinate system that are equal to 0. So in this sense, it's static, it's not moving, this observer, and is the way to define a static observer. The only difference is that it is an observer, so since it is an observer, his for velocity must be normalized to 1, to minus 1, the norm of the for velocity. So this means that I have to rescale in general the killing vector, because the killing vector is not obliged to satisfy this property. And in general won't do it, because otherwise this could create somehow the fact that here there is a v, which is a function, is important also to satisfy the killing vector equation. And why I introduced this normalization, because I want that u mu is equal to minus 1. Okay. Okay, so now why I introduced the static observer? Because the static observer will be my mass that is held fixed at the surface, essentially. And the next goal is to try to covariantize the Newtonian expression that I've written above. So in order to do this, then I have to introduce the acceleration, the quadric acceleration of the static observer. And notice that now it takes the same form as the geodesic equation, but now it's not 0, because this observer is not an observer that is really freely falling, it's really the opposite. So because it is constrained to stay in a given position, so we are not considering anymore a free-falling object, so this quantity is different from 0. So there is really an acceleration in this particular context. And the acceleration will be evaluated as follows. Yes, by the way, nobody maybe complained, but what I have here is just the covariant derivative which is associated to the Levi-Civita connection. So for the moment, I'm really in a very basic standard GR setup. Okay. And this quantity I just used the Leibniz rule. I didn't do anything special. But the interesting part of the story is that thanks to the fact now I start to profit from the fact that this observer is really a static observer. And in particular, essentially, I can prove that this term is equal to 0. So you can do it in several ways. So one way that it's well, relatively, that is not the important part of the story, but it is relatively easy to handle, is the following. And I just profit from the fact that v square is equal to the norm of this object here, and then I reconstruct the Killing equation, which is equal to 0. So that's probably the indices here are a bit small, but it's just I just essentially recover the Killing equation in order to say that this second part of the quadri acceleration is equal to 0. So I just get here what is important. That is just a small computation. So the things that matters is just that C mu. And here for the first time, so we will use it in several places. So this is true thanks to the Killing equation. That will be really crucial. So why I can do this only for stationary space-time? Because in several places I will be forced to use the Killing equation in order to arrive at the final expression that I want to consider. And okay. I'll go here. So now there is just a small thing that I ask you to buy, and it is the fact that after I computed this quadri acceleration, this is something that I can define on any sphere that is outside of a source. But I will be interested in comparing it with a force that I will have to use at infinity to keep the body static, and this force is redshifted by a factor of v. So there are some ways of getting it. There is a sort of Gedanken experiment where you have to use a very long massless rope, essentially, to keep the body attached to you for the observer at infinity. So it's not the main point. I don't want to spend too much time here. So, but that's, well, I warn you that it's something that I ask you to buy essentially for free. But if you accept this, then you see that the force at infinity that I need to use in order to keep this observer fixed is just so essentially the expression, the analog, the covariantization of expression that I've written there is something that takes this form here, where the difference with respect to what I've written there is essentially that instead of having a v square, here I have just 1 power of v. And Now, the interesting thing is that in this particular case, both xi mu and are both orthogonal to the sphere. And yeah, maybe something else that I should have stressed. So this sphere is really computed as a sphere, which is really, it was manifest where I integrated in my small example. So it's a sphere that fixed radius and fixed time. So it's really a two-dimensional sphere in a four-dimensional space-time. Okay, so here I have two vectors that are orthogonal to the surface of the sphere. So one is the outward radial direction, and the other one is my time-like killing vector. Okay, but since I have these two vectors that go outside, eventually I can rewrite this expression in the following form. So this is just an integral of a two form because I'm really integrating over the sphere, and it's an integral of a two form where these quantities here are orthogonal, essentially are the two directions that are orthogonal to R and T. Okay, so the fine details of what I'm doing are maybe not so crucial. Well, we can discuss later if I'm going a little bit faster, but at the end of all this small discussion, I will try to summarize what are the important ingredients of this formula that I'm gonna derive. And okay, so what's nice here is that we started from a Newtonian expression, and we got a counterpart which is completely covariant in this particular case. And the ingredient in both cases was an integral over a sphere at fixed r and fixed time. Okay, and now there is another important observation, and I got a specific expression. So that is the covariantization of what I've done before, and it is what it is. And now I already we already appreciated that in order to arrive to this final expression, I had to use the killing equation. So it was really important that xi mu is a time-like killing vector. But there is another important property of this quantity here, which must reflect a property that I have in this particular case there. So there is really like Gauss' law, thanks to the fact that the Newtonian potential satisfies the Laplace equation. I can change the size of the sphere and nothing changes, essentially, because you will have, if I change the size of the sphere, I will have to change terms by the divergence of this, the divergence of phi, which just give me the Laplace equation. So it's precisely as in the Gauss law. So as soon as I am outside of the source, I can choose whatever sphere I wish. So one thing that we have to check if this is true also in this particular case. But how can I obtain a property of this type? In order to get this type of property, I must have that the two form that I have here is conserved. So this means that if I act on the exterior differential with this two form, I must get something that has an exterior differential which is equal to 0. So this object here that I introduced is just an alpha beta wedge. Dx beta is a two form. Okay, and this integral won't depend on the surface on which I'm integrating upon. If and only if the alpha is equal, the exterior differential of these two forms is equal to 0. But now I define it, let's check. Either it is equal to 0 or it is not. Let's see what happens. Okay. And so we can check if exterior differential is equal to 0 or not. To this end, it is convenient to use a small trick. To define the exterior differential, I have to antisymmetrize this object over the indices. To make the antisymmetrization manifest, I contract it with the epsilon tensor. That will be a useful trick that we will also use in the following. So this is my two-form, and notice that this two-form depends on the antisymmetric part of this combination, which is precisely the one that is not set to 0 by the fact that this is an isometry. So at least it's coherent what I got. And now, in this particular current context, what do you have? So you have a contraction of two epsilon symbols. But the contraction of two epsilon symbols is just giving you a bunch of Kronecker symbols. And indeed, this object can be rewritten in the following form. But here I can use the Killing equation, and this means that I can flip these two indices thanks to the Killing equation, and therefore eventually I can rewrite everything in the form okay. And now, how can I got this identity here? Is again a consequence of a Killing equation, because one consequence of a Killing equation is the following. So this is an identity that has one derivative more with respect to the Killing equation. How do you obtain it? You take your Killing equation, you act with a covariant derivative, and you take a trace. And this is the result that you get, and you have to compute this Ricci tensor comes because you can perform a commutator of two covariant derivatives in this expression. So I leave it somehow as an exercise, because again, it's not the most important thing here. But what we discover? So we discover that here, so we have a exterior derivative of my two-form, and this exterior derivative of my two-form is proportional to the Ricci tensor. But we are in the vacuum because we are outside of the sources, and outside of the sources, this expression is equal to 0 when the equations of motion are satisfied. So eventually we discovered that, well, that's was not precisely the case, but we got that our two-form is conserved on shell. So you see that we are recovering a situation similar to the one of that we have seen in the case of the Noether tensor, but with an important difference that now I'm not integrating anymore a current of a Recauchy surface, but I'm integrating, in this case, a two-form. In general, it will be a d minus 2 form over a surface of codimension 2. So which will be the correct way of defining charges in general relativity. And so the end result, which is the important thing here, so I didn't want just to really get the formula out of the blue, but the important thing for the sake of the discussion will be the final result. And this is the Komar mass formula. Or if you wish, the Komar mass. Okay, so, and some detail was not completely clear. You can, as I anticipated, so this is just coming from a good old book by Wald, and you can have a look for additional details or for different details, because maybe I make more explicit some steps that were not explicit there, but some other things can be that are detailed in a better way there, maybe. And here does not depend on S. On the surface of integration, provided that this is killing we are on shell. So, and that is so I promised that this was just an example to try to understand what are the features that we have to look for in our quest for conserved quantities in general covariant theories. And the two important observations are here. So these formula for the mass depend on a time-like killing vector, essentially, and it includes inside an object which is a two-form, and this two-form is a function of a killing vector. These two forms satisfy a conservation condition, a non-shell conservation condition. Okay, so our goal in the following will be to try to extend to develop more general formulations with respect to this kind of bread and butter way of trying to define a quantity that satisfies this property there. Yeah.
Once again, where does it enter the fact that the killing vector is time-like?
That is time-like, well, it's not important, so I think it's just for the fact that you want to interpret it as being an energy.
Okay, this is okay.
Yeah.
At the formal level, if you have a killing vector which is not time-like and you proceed with extraction,
I think you should be able to find, I think, so that's, I'm not 100% sure, but there should be an analog of this that defines for you angular momentum. And there you should take into account also other type of killing vectors, I would say. But there you have to find a situation in which you can define the angular momentum. Here the advantage is that if it is a time-like killing vector, you profit from the fact that you can interpret it as being a static observer and all this kind of stuff. But I think that formally, no, it's not a problem. And indeed, the next step will be really to extend this kind of construction to arbitrary killing vectors to begin with. And then we will see that this is not enough because generic spacetimes do not have any killing vector. So we will be forced to do something more, essentially. But just to try to wrap up, what are the key properties here? So somehow there is a sort of general result or general lesson for the moment. In gauge theories, conserved quantities are given by expression of this type. So we have a certain charge Q, which is the integral on the boundary of Cauchy surface, or generically on a surface of codimension 2. But to fix the ideas, you can think at the boundary of a codimension 2 of well, here I denote by n the dimension of space-time, just not to have too many d's around, by this object here. And this object here is a d minus 2 form, because this object is defined to be so here you have the indices mu nu that are free, and then you saturate the epsilon up to n minus 2. And here you just have the x alpha 1 wedge dex alpha 2. Okay, so it's like, this is a sort of, it's called Hodge dualization. For instance, instead a Lagrangian, I can interpret it as the integral of a Lagrangian density with a volume form, or just the integral of a volume form. And similarly, the integral of a current, it could be interpreted as being the integral of a d minus 1 form. And in this case, I have a d minus 2 form. And with the property that dk will be equal to 0 on shell. And if this property is satisfied, then this quantity is manifestly invariant over the surface that I use to integrate. And there is a general, I don't have much space, something which is called as generalized Noether theorem, which has been established by Barnish, Brun, Ternot. In 95, if I'm not mistaken. And is telling you that this kind of n minus 2 forms such that dk is on shell trivial, they are in one-to-one correspondence with parameter, the parameter of symmetries that leave the fields invariant on shell. Okay, so this is just a generalization of what we have seen this is a generalization of a Killing equation. So in the case of general relativity, the field is the metric. Say that I have general relativity in the vacuum, and a diffeomorphism generated by a Killing vector is a diffeomorphism that is not modifying the field on shell even. So in the case of a Killing vector, we don't even have a problem of being on shell, so that is a setup which is a bit more general. So this means that if I classify these, I classify that one. But, well, rather than entering into the details of this theorem, well, maybe let me do an example then, and then I will comment how powerful is this result, if any. So, let me first make an example, and then I will comment more about this result. And the example that I want to make is even simpler than the case of general relativity. It's just a Maxwell theory. It will be much clearer, I hope, what I'm saying here. In this example, what are the transformations that I have? Are just the gauge transformation of the vector potential. Okay, so these are the transformations that I have into the game. And so this lambda here, well, sorry for my handwriting, it's not just this lambda there, are just this gauge parameter. And indeed, well, let me make explicit that here I have a dependence on the space-time coordinates. And here, as you all know, a priori I have a dependence on the space-time coordinates too. And now I have to look at the transformations such that delta lambda A mu is equal to 0 on shell. But what are these type of transformation that preserve the gauge potential? So here I have a derivative. Essentially, I have constants plus transformations that are equal to 0 on shell, gauge parameters that are already equal to 0 on shell. So a priori, I can have a dependence on the gauge parameter by the field. This is a situation maybe we will comment later, but just to be, for the sake of concreteness, this condition implies that this object must be a constant. And what is the conserved 2 form which is associated to this constant? For the moment, I'm not deriving it. I'm going to do later. So this is a kind of overview or of the kind of quantities and objects that we are going to introduce. But for the moment, I propose to, I ask you to trust me or to verify that my answers are correct better. That is maybe more appropriate. So in this particular case, the conserved 2 form is just given by the field strength. And again, so this object here, in this, if I'm in generic dimension n, is an n-2 form, and it is obtained just by contracting this object here, which is an n-2 form, which has 2 free indices because there is hiding an epsilon tensor inside with a field strength. And the dependence on the parameter here is just this constant c. Okay. And in this particular case, what you can check is that if I repeat the same trick that we did for the case of in the case of a Komar mass, let's do it just to avoid writing a huge bunch of indices. Let's do it just in d equal 4. Okay, this is kind of general rule. So if you have if you want to have a n-2 form which is conserved in the sense of having an exterior derivative which is on-shell trivial, this is completely equivalent to have a divergence of this antisymmetric object equal to 0 on-shell. Because how do you move from one to another? By making a contraction with the epsilon symbol, because this object inside contains, sorry, this is not K, it's probably what before I was calling alpha. Sorry, this is more correct. There is an epsilon symbol that is hidden inside, and the contraction of the 2 epsilon symbols brings for you an exterior derivative. Or you can even do the things the other way around. You can start from the antisymmetrization with the exterior derivative, and you contract with an epsilon symbols, and you reconstruct the other relation. So the important thing is dk equal to 0 is always equal to the divergence of k mu nu is equal to 0. And it's just a matter of contracting epsilon symbols. Okay, but then this means that this quantity has the right properties that I announced you as being the properties of an object that I can use to define a charge. And based on this, I can define the electric charge, which is just this object defined for k equal to, for c equal to 1. And well, okay, maybe, yeah, I should have used another name. C is not clearly the speed of light. It was just an arbitrary constant here. And this quantity here just become, if you make explicitly, if you express the spin connection in terms of the electric field, and the magnetic field, it just becomes the flux of electric field around the surface. So it is precisely Gauss' law, what you have recover in this particular way. So it's just something very standard, obtained in a apparently very complicated manner, but is just stressing that also behind the usual Gauss' law, there is the conservation of a n-2 differential form. And yeah, and if you wish this object, you can also write, if I pick up a form here, I have chosen to integrate over a sphere as a certain radius r, and this is completely equivalent to take so maybe in this way you can appreciate why I'm introducing such a apparently cumbersome notation. The fact is that if I always integrate over a sphere at fixed t, at fixed r, that is useless cumbersome notation, but is a notation which is completely invariant. So I can integrate over any codimension 2 surface. In this particular case, so it's more general and is more covariant also. And maybe the last remark about this quantity here is that, well, we can even check explicitly based on the properties of this quantity that I introduced that the electric charge is conserved. Again, so I'm just rediscovering something that we all know very well. And since I recovered Gauss' law, it should be obvious that this charge is conserved, but it's instructive to see why in this particular context. And the idea is that if I just take a derivative in time of this object, this becomes just dt ktr dn minus 2 x tr. And since this object is conserved on shell, is what we discovered here, eventually I can rewrite this term as being minus the integral over the same sphere of dA kAr ds. And this is equal to 0 on shell because now I have a total derivative that I can, is a total divergence, and then it becomes a pure surface term. And this identity between the two just came from the fact that dt ktr plus dA kAr is equal to 0, and capital letter means here just angular indices. Clearly, as soon as I don't cross sources, I can do precisely the very same computation for the derivative in dr, which means simply that I can change the radius of the sphere and nothing changes, provided that I do not cross sources. So at some point, it doesn't hold anymore because I hit a source which is inside the stuff. So it seems that you are going into the right direction, although we have still we need to find a systematic way to produce this n-2 conserved form. But in the case of general relativity, we immediately hit a problem that I already anticipated. It is the fact that the generic metric doesn't have any killing vector. So there is any isometry. So in general, this space here is empty, which seems to mean that we have no charges at all. So this theorem is very nice if I want to define conserved charges for classes of solutions that have a certain isometries, but in a sense, I can use it to generalize what I've done for Komar mass. But in the case of a static solution, the best I do is just an abstract way of recovering something that I already built, the Komar mass, because I need to have this kind of solution. So the next step will be to try to go beyond this. And what is the way out to this kind of situation? The way out is that to define this kind of quantities, what I can do is just to put myself at infinity, or put the observer at infinity, essentially, and be in a situation in which I don't have an exact conservation law. So if you wish, I don't have an exact killing vector, but I have something which is just an asymptotic killing vector. So something that satisfies the killing vector equation, but only at infinity. And correspondingly, what I'm going to do is that I will try to take this integration over surfaces with our sphere at infinity. So we are going to push the same type of construction at infinity. This brings to the concept of asymptotic symmetries. Asymptotic symmetries are just symmetries that are asymptotically true, but they are not true everywhere. So a Killing vector is associated to an isometry of a metric, so is a symmetry of is an isometry, so it's a symmetry of a metric at every point in the space. That's essentially there are no way of getting a situation like this in a kind of a generic situation, but we can have isometries that are only asymptotically true. So this means that the next step will be a little less formal. So I haven't proven this theorem, but you can say it's a theorem, so it's a solid result. Everything that concerns asymptotic symmetries starts to become a bit less solid because you have to develop a setup in which you try to fix some boundary conditions. So you decide what is your configuration space, and then you look for symmetries that preserve this configuration space asymptotically. And we will see that also the way of defining charges could become a little bit tricky in this particular context. So what I propose you now, yes?
In that situation, why is that factor of 2 in the
Yes, the factor of 2. Yeah, thanks. Here, I think I just lost. Okay, thank you. And what I was then in order to appreciate the subtleties that are related to this concept of asymptotic symmetries, the next step will be to move to my sort of warming up example. So instead of working in gravity in 4 dimensions, I will reduce the dimensionality of space-time. I will go to gravity in 3 dimensions, and I will develop a series of techniques that are very three-dimensional, as I anticipated, but they have an advantage of letting you, I think, understand in a clear way what is the difference between an asymptotic symmetry or a global symmetry, a proper gauge symmetries, and so on and so forth. And that's I won't elaborate much more in the following, but why well, we are going to see, but why 3D is clearer in a sense, because in 3D it's very easy to establish an Hamiltonian formulation for gravity. So essentially understanding what is an energy, what is an angular momentum is something that is kind of natural in an Hamiltonian formulation where you really have time, and then you can really set up charges that are associated to time translation, even asymptotically. But the Hamiltonian formulation of gravity is somehow more complicated, and the road that I will explore, so this kind of covariant techniques, takes really the opposite way. So they try to formulate things which are covariantly. The price to pay is that they are more abstract, and so in order to first consolidate the concepts that we will try to generalize in the covariant space formalism, we are going to touch them in a very concrete way in 3 dimensions. So since there will be a kind of switch of subject, do you have any question about this long introduction? Yeah, so that's it's important to interact. Now it will be a bit more streamlined, the 3-dimensional case, but all the key ideas are already here, so it's important. Sounds crazy, reasonable but confused. So we're gonna see. So which one? This one? Here? This one? This one? Yeah, that is just a gauge symmetry of Maxwell, but in a sense you can interpret diffeomorphism as being a gauge symmetry of gravity. So in a sense, this is just a baby example of a killing vector. So it's a case in which the analog of a killing vector equation, sometimes they are called reducibility parameters, the solution of this kind, these parameters that leaves the field invariant. But that is the most generalization of killing vector in any theory. So if you have a gauge symmetry, you can look at gauge symmetries that keep the field configuration invariant. And that is really the simplest example. Next step is the killing vector equation. But you may even have gauge symmetries that are much more complicated. But if this gauge symmetry is keeping the field configuration invariant, is a reducibility parameter, and there is a conserved charge associated to it. It doesn't have to be a space-time symmetry. So it could be whatever gauge symmetry. So it's no, it's a very general. So nothing to do. Well, it's often used in the context of general relativity. But why? Simply because here is really a clear overshooting. So because I can do everything which simpler techniques. So that is, yeah, so you can do at high school almost to define what is the charge. While for general relativity, you need a little bit more of techniques to be used somehow. Please. Ah, okay, so this is my handwriting, so it's, yeah, sorry. So it's Barnish. Let me try this way. Maybe if I write like this, it's clearer. Brand. And no. Well, they have several papers together. Well, I don't have in mind the precise reference, but we can discuss it. So I'm not even sure that 95 is enough to distinguish what is the right one, but more or less that is the period. But for instance, for this kind of techniques, so you can look at the lecture notes that I was suggesting by Compare and Fiorucci, and all these references, you can find the precise reference to that one, to that particular stuff. Okay, so if there are no other questions, I will move. How much time do we have? Yeah. Yes. Okay. Okay, I'm very slow, by the way. But let me. So this means if I have only 20 minutes, probably I won't have time to enter into the details of how to compute the asymptotic symmetries, but it will be for tomorrow somehow. But let me at least introduce the topic of three-dimensional gravity. So essentially, why three-dimensional gravity is special? Well, one way of seeing it is that you just look at the Riemann tensor, and you can decompose the Riemann tensor in its traceless part plus traces. Let's see, if you wish, alternatively, you can think of it as being the definition of a Weil tensor. Okay, so the Weil tensor is just the traceless projection of a Riemann tensor. And this is in dimension n to begin with. Yes, so n is equal to the space-time dimension. And the first information, important things to notice, that this is nothing to do with 3D gravity, but it's just the fact that on shell, we have that the Ricci tensor is equal to 0. But if the Ricci tensor is equal to 0, this means that on shell the Riemann tensor is equal to the Weil tensor. What does it mean? This means that the Weil tensor is carrying all the information about the solution that we have. There is radiation or there is no radiation is the Weil tensor, who knows. There is a potential, an attractive potential, again is the Weil tensor, who knows, inside this, because the other part on shell is trivial. But in 3D, there is something very special that happens, and it's just that this object, it is identically 0. So how can you understand this? One way is that, well, there is a general result that tells you that if you have a tensor which transforms under in a reducible representation of OD, so this tensor can be associated to Young tableau that always have the dimension if the number of the number of columns of this object is bigger than the dimension of space, than half the dimension of space-time, then this representation is equal to 0. And this Young tableau is describing the symmetries of a Weil tensor. If you don't want to resort to this generic result, you can just do an exercise and you put inside the components 0, 1, 0, 2, because you have 0, 1, 2, the only one that you can put inside, and then you use all the symmetries of the Riemann tensor, and you discover that you cannot write any component which is different from 0, essentially. So in practice, this general result is just telling you that if you put 0, 1, 2 inside all this combination, there are always some identities that set this guy equal to 0. So it cannot exist. There are no non-trivial components that you can write in this particular case. But if this is 0, this means that if I impose Einstein equations in this particular space-time dimension, I find that, and in this case I'm working with Einstein equations with a cosmological constant, I find that, well, just to fix the notation. Then I can substitute this information inside R here, and or if you wish, I can substitute this information inside this term, and I will find that also the Ricci tensor is fixed in terms of a metric. And the final result is that by substituting everything inside here, is that in 3D on shell, essentially all solutions of Einstein equations are locally spaces of constant curvature. And then you can tell me, come on, are you crazy? So you are talking about nothing, because there is nothing here. This is not true, because this relation is true locally. And indeed, we will see that even in this particular case, we will leave a very rich structure of asymptotic symmetries and conserved charges, with a great advantage that I don't have all the mess that is brought by radiation, because the radiation is definitely not there. But the solution, so I won't have time, or is not the main goal of these lectures, the space of solutions in presence of a positive cosmological constant is particularly rich, because even if all solutions are locally anti-de Sitter in this particular case, you may still have black hole solutions. Then you can say, how is it possible that you have black hole solutions if the space is everywhere of constant curvature? The fact is that the black hole solutions are obtaining by making identification of points inside anti-de Sitter. So there are really non-trivial solutions that are brought by a non-trivial topology. And these solutions looks like a black hole in the sense that there is an event horizon. And the only difference that the event horizon, of course, is cannot screen singularity, as in the case of 4 dimensions, because there cannot be singularities, everything is of constant curvature, but is screening what is called a chronological singularity, since that I have some identification of points that I have to do, and at some point this identification of points creates closed time-like curves. And so the horizon is screening essentially the exterior of a black hole from the point in which there is what is called the chronological singularity. So there are many reviews of these topics. If you are interested, you can have a look. We can discuss separately, but I'm not going to discuss. But so this is just to say that the space solution is already non-trivial at this point. And the other thing is that we are talking, as I anticipated, about global structure. So I can introduce a very non-trivial space just by fixing suitable boundary conditions at infinity. So it's a theory that contains nothing, but only locally. So if I look at global properties, there is a very rich spectrum of solutions. And a priori, if I just do this, I apparently don't gain much. So I will still have to introduce all the machinery that I will develop in the following lectures. And in some lecture notes, you really see the reverse logic. So people first develop the general strategy, the general machinery, and then they apply it to this particular example to test it in a simple context. Here we'll do something different, and we profit from the simplifications that we have in this context to try to elucidate the concepts that we need in the simplest possible example. But still gravitational, essentially. And in order to do this, to develop these techniques, here I'm going to do something different with respect to what I will do in the following, and I will work in the first order formulation of general relativity. So up to this point, I assume that all of you had the class in GR. Now, are you familiar with the first order formulation of general relativity? So someone not familiar? Okay, so just briefly, so here, instead of working with the metric G mu, what we are doing is to work with a different set of fields that are called the Filbine and the spin connection, essentially. So it's a different field content that describe precisely the same theory. And how the two are related, well, say that in this context, if I have E mu, I can recover the metric in this particular way. That is a kind of cheap way of introducing the first order formalism of general relativity. There is also another way of characterizing it. What I'm doing and what I've done up to now was to work in the coordinate basis. So for me, a basis of a tangent space at a given point in the manifold up to this point, and in most of the basic courses, it's just provided by the differential in a given chart. So I set up a coordinate system, I take the differentials, and these are the basis vector of my tangent space. And you can see, because tangent vector can be interpreted as linear functionals acting on functions in a given point. But in practice, this is what you have in most of the courses, but I'm not forced to stick to this basis, so I can change basis. And one thing that I can do is just to introduce a new basis of my tangent space. And the advantage, I want to introduce, yes, and the property of this basis here is that I introduced a base of vector which is orthonormal, essentially. And I'm playing with orthonormal bases at each point in tangent space. But for the sake of concreteness, we can just don't care much about it and just say that I tell you that there is another formulation of general relativity in which you can use these two fields. And the point is that the equations of motion that I can draw from this action here contain an equation of motion which is of this form. And if you look at this equation of motion is algebraic in the field called the spin connection. So I can solve for it. I can write the spin connection as a function of the field line, take the field line, plug it back inside the action. I have a right to do, because I'm solving an algebraic field equation, not a differential one, and the result is your beloved Einstein-Hilbert action. So it's just a reformulation. It's a very convenient reformulation of general relativity, which for us it will be just convenient. In some contexts is even very important, because for instance, if you want to couple fermions to general relativity, you need this formulation. Why you need this formulation? Because fermions are described by their transformations under Lorentz transformations. You need at each point in tangent space to have a formulation in which Lorentz transformations are implemented. Otherwise, you won't be able to couple fermions to gravity. So in this sense, it's even more fundamental. But for what I have to do, it would be enough to just think of it just as a convenient reformulation of general relativity. And okay, so oops. What else? Then what I've written there for you is in 3D, because you see that there is an epsilon symbol with 3 indices. But what I have written there is something that you can generalize in an arbitrary number of space-time dimensions. So essentially, you just take a wedge product of additional field binds in front in order to arrive to have a volume form. But in 3 dimensions, there is something nice that happens. And I can dualize the spin connection, because I can introduce an object. And as a result, yeah, by the way, I haven't, sorry, this is something that I should have done. Here, for people that are not familiar, I should have defined what is RAB. And RAB is just this one, the curvature. So in general, people say that what I'm doing, you see this look like a Young-Mills curvature for the spin connection. Indeed, it is really a Young-Mills curvature if you take a field that takes values, say, in the Poincare algebra. So this reformulation is almost like a reformulation of gravity as a gauge theory. It is almost a reformulation in 4 dimensions, but it is a reformulation of gravity as a gauge theory in 3 dimensions. This is the advantage. Why I will profit from it? Because it will allow me to teach something about gravity, starting from a formula that holds in a gauge theory in which computations are easier, in a sense. Yeah, sorry, that's true. Thanks. So you have to remind me that sometimes I don't define all the things that I introduced. L is just the ADS radius. No, it's not Planck scale, it's the ADS radius. So I'm already in the case in which I have a cosmological constant here. The cosmological constant is equal to L to the minus 2. Okay, and there is no problem. So it's just because the space of solution which is more interesting or easier to attack is the one of a positive cosmological constant. You can send L to infinity and nothing changes. Everything that I'm gonna say is still valid in this particular context. But thanks for the question. Do not hesitate if I forgot to define something, because it's important. Yeah, just a small exercise of dualizing the things. And with this new, after I implement this dualization, the Einstein-Hilbert Lagrangian, I can write it like this. So this is a kind of nice intermediate step. So you see in the term with the cosmological constant, I didn't do anything, I just copied it. The other term, I just dualize it and reformulate this particular term.
So R with 1A is the dual of RAB?
Yes.
It's not the curvature for...
It is also the curvature for omega, but in particular, you can obtain it by dualizing the other R. Yes. So if you do exactly the very same definition as this one, you do the computation and you find this term. Okay. So for the moment, I just played. Maybe one thing that I can point out, I could have done even above. I told you that this is an equation of motion, the torsion is equal to 0. This is an equation of motion that you have in 3D and higher dimension. It's the equations of motion which allow you in any space-time dimension to eliminate the spin connection as a function of a field bind. Here I have something interesting instead that is happening. Well, interesting, from some respect, very boring. But the other equation of motion is this one, that is just telling me that all solutions locally are spaces of constant curvature. So it's boring, but it's not surprising. It's the same problem that I had before. And now the interesting further step is, yes, so before going for the last step, an important observation. And the important observation is the following. So what are the symmetries of this action? One is something that at least who is familiar with the first order formulation of gravity should recognize. Say this part here, ignore for a while this one that I already written, sorry. But this one is the transformation of a spin connection. And this type of transformation is using a Lorentz covariant derivative that is just defined like this. Yes, so is FB lambda C. So this transformation here is just the usual transformation of a spin connection in dualized form, because the spin connection is a gauge connection for the Lorentz transformation. So remember that I introduced this orthonormal basis. So I really wanted to implement Lorentz symmetry locally at any point in tangent space. And I have local Lorentz transformations in this formulation. So in Minkowski space, I can only do a global Lorentz transformation. If I turn, all the space turn with me. Here I can turn independently in any point of space-time. And it's just, if you wish, a reformulation of the inertial principle of the fact that locally I can always find a coordinate system in which my space-time is flat in a sufficiently small ball around a given point. So that is not a surprise, at least for people that are familiar with the first order formulation of general relativity. But here there is a surprise. Because what this means that this theory is invariant also under local translations, and this is not true in 4 dimensions. In 4 dimensions, the only symmetries of the action are local Lorentz transformation and diffeomorphism. Here, diffeomorphisms are still there because I've written everything in terms of differential forms, so this action is manifestly invariant under diffeomorphism, but it seems that I gained one additional symmetry. So what's going on? So is it gravity, this stuff, or it is not, because it has an additional symmetry? Actually, the additional symmetry is not really a new symmetry in the sense that one can check, and is a good exercise that I leave to you, that if I define a local translation parameter in this way, introducing, so here, this is a tangent vector written in terms of these tangent space indices, and this is just a good old vector with base manifold indices. If I introduce this kind of object, then the variation of the field bind takes the following form. And where this is true, up to local Lorentz transformations, that I don't care, and on shell. So I have to use the equations of motion to do this. Well, let me write it like this, since I can profit from this, from the presence of this particular term here. So this means that actually I haven't multiplied the symmetries. These are just the usual symmetries of gravity, but I gained something important in the sense that now a very complicated symmetry that will let us to struggle in the next lectures now is implemented in a very simple way. And this is yet another reason why here I can handle easily the definition of certain concept in this case. And then yeah, just one to conclude, and then for the symmetries we'll go tomorrow. Yes? Okay, so because, no, luckily they seems to be correct. So this is a mu, this is a mu, yeah, good point. Voila. But this is just a diffeomorphism. So it's the Lie derivative of an object which is a one form, because with respect to Lie derivative, is index A is completely inert. It's not doing anything. So think at the, so if I'm making mistakes, correct. So you have to think just a Lie derivative of a one form. And now just to conclude, now, one thing that I can do is to introduce an object. Well, here I'm even picky with dimensions. Yes?
Also, in the report, there, so variation of ERA, yes.
Yes.
There's a E missing in the very end or the sign? Very end?
Here?
Yes. So
Well, at least indices are from, no, indices are correct. No, it's not a wedge product, this one, because this object here is not a one form. So then I don't need the wedge product here. So this object is a one form. This object is a zero form. Acting with a derivative, it becomes a one form. Okay, and this object here contains a one form and a zero form. Yes, thanks for the other precision. So here at some point, all the objects that I've written there, so it was manifest from the fact that I was writing a wedge product, are typically one form, but the gauge parameters are zero form. And this parameter here is just, again, the dual of a Lorentz parameter. A Lorentz parameter should be a lambda AB. I can dualize it, and I get just a lambda C. And then I can introduce this particular one form, because this object is a one form, this object is a one form, this object is one form, and now I contract them with the generators of an algebra, and the generators of this algebra are just the generators of the isometry algebra of a vacuum. So these are just the usual generators of Lorentz transformations, dualized. So these are three-dimensional Lorentz transformation. If you do the counting that you have done this morning, you do it in 3 dimensions, and you discover that you don't have 6 Lorentz generators, you have 3 of them, and I can dualize them in a vector. And these are just the generators of translations. So this is just the fact that translations transform under Lorentz rotates. And this is the commutator of two translations. If L goes to infinity, this is just the Poincaré algebra in 3 dimensions. If L is real, this is the anti-de Sitter algebra in 3 dimensions. And it is, and if L is imaginary, L squared just changed sign and becomes the de Sitter algebra in 3 dimensions. So this algebra, depending on the sign of L, it could be either ISO 1, 2, SO22, or SO12. Yeah, no, SO13. And then the final things, and then I stop. An exercise that you can do is to check that the Einstein-Hilbert action can be rewritten in the following form. And this is what is called the Chern-Simons action. With algebra, which is two one SO22 So as I anticipated, in 3 dimensions, gravity, it is a gauge theory, and in particular, it is a Chern-Simons theory. So then I will stop here, and then we'll see the symmetries of this action tomorrow. Okay, thank you.
Okay, very good. So now we have a break, and I would suggest since we have questions and answers soon, we can postpone also questions that we have in mind. Let's take a 10 minutes break, and in 10 minutes we are here. So we divide the questions and answers into 2 sessions. We start with Andrea, and after Andrea, there will be questions from Ellie. Okay, 10 minutes please.
Alla fine.
Ti potevi risparmiare questi 10 minuti per domani? Ti potevi risparmiare questi 10 minuti per domani?
Non c'avevo l'orologio perché mi sono scordato, quindi non sapevo dove stavo, se mi davi il dato.
Io cercavo di dirtelo per aiutarti. Vabbè, purtroppo mi sono perso le prime 7-8 lavagne, perché ho questa consegna della tesi oggi, devo finire di correggere le cose, poi vabbè, che mi interessa sta cosa. Se no non lo capisco, ma perché ci sono oggi? Ah, questo è io, ok.
Di solito scrivo meglio la lavagna.
No, è chiarissimo, perché non lo vedevo io. Poi secondo me potevi anche giocare un po' meglio la parte su gravità con la teoria di Gauge, che potevi dire qualcosa di più, perché secondo me non la sapevano bene. La parte più generale, per esempio la torsione, gli potevi dire dove viene fuori la torsione, per guadagnare un po' più evidente. Anche perché secondo me non è molto usato.
Quello lo posso anche recuperare domani. Diciamo, questa è la parte col pilota automatico, no? Quindi, che ho messo davanti in realtà perché ci ho provato a farlo in modo diverso, ma non c'è senso. Perché a questo punto non c'è senso fare gravità in 3D soltanto per testare delle forme di computazione estreme.
Quindi qui il punto è che questo è un ecomorfismo, è la stessa cosa che accade quando la curvatura è zero, essenzialmente. Che il diffeomorfismo, il punto è questo, il diametro di curvatura è costante.
Lo vedi qua, perché nella teoria di Chern-Simons quell'operazione che fai è esattamente quella solita per vedere come sono realizzati i diffeomorfismi di Chern-Simons.
Cioè però diciamo su ADS4
E non lo puoi fare su ADS4.
anche se la curvatura è costante, no?
Perché Sì, però il fatto è che qua sono tutte le
Il
configurazioni.
fatto è che, esatto, ci
Poi
può
tutto
veramente
lo-
una teoria formalmente diffidente,
Esatto.
e che senza imporre le equazioni del modo ci accomuna una cosa.
No, no, le equazioni del moto le impone,
Poi le devi provare,
però
le devi
non scegli
imporre.
una soluzione sola,
Però
ma
le
è
devi
tutto lo
imporre.
spazio
Sì,
delle
cioè,
soluzioni.
esatto, non è che ti restringi a
Esatto.
quelle soluzioni. Cioè,
Questa
qualunque
è-
soluzione a cui puoi dare costante.
Esatto, che è la differenza rispetto agli S4, perché è chiaro che se tu scegli una soluzione poi hai le stesse cose, ma qua ce l'hai in default su tutto spazio delle soluzioni.
Un'altra cosa che potresti dire con un po' di tempo su quello di tre, gliel'hai detta, però non gliel'hai detta in questo modo, che non ci sono gradi di libertà che si promuovono nei casi.
Sì. Sì, diciamo, tanto avendo spezzato a metà, si può fare il summary. Sai, alla fine questa qua è un pochettino molto
No, ma anche tutta la parte
settoriale.
iniziale.
Che definisci la derivata della contramassata.
Bellissimo, non è scritto mai
Posso fare un cane, quindi della che giochi, sì, però è stata una cosa su cui questo qua, semplicemente quello che ho fatto, mi sono ricopiato le formule che
Certo, hai fatto più fatica, è una
la
cosa
massa di
generale.
comando,
Certo.
perché quella devo capire come era definita, cercare di farlo in un modo, e già ci sono dei pezzi, quella cosa del reshift, comunque l'inglesissima,
Anche appunto Walton Street, ma perché c'è chi ritiene una cancellazione degli anni 70, per loro la verità era geometria differenziale. Loro facevano geometria differenziale.
anche se in questo caso è proprio il contrario, no? Perché c'è gente tipo il libro di Poisson che fa la massa di comando in un modo assurdo, Poisson, e non è male per alcune cose. Lui ha fatto, si chiama Toolkit for Relativist, che dovrebbe essere un libro un po' più avanzato, però lui aveva fatto una cosa simile a questa, l'ha fatto in modo serio, ci ha scritto un libro per Cambridge University Press, e lui la definisce partendo dal come fai se vuoi in Maxwell, no? Che tu parti dalla corrente elettrica conservata, usi le equazioni del moto e la riscrivi come in funzione di F. E quindi lui parte dal tensore energia-impulso, te lo riscrive con le equazioni di moto, fa sparire il tensore energia-impulso e poi ti dice questo è valido anche fuori da dove non c'è il tensore energia-impulso. Ma sembra già complicato. Mentre come lo fa Wolf, questo è molto fisico, perché lui c'è anche una cosa che dice l'espansione in multipoli, queste cose qua che cioè che
Non mi ricordo, Walton, questa cosa?
questa qua la fa Wolf,
Con l'espansione multipoli?
fa anche l'espansione in multipoli, ma lui la menziona soltanto.
Quando fa la picking property?
No, proprio quando definisce la massa di comando.
Forse
Dice che l'altro modo di definire la massa di comando è come in termini di monopolo, un'espansione di multipoli, però lì devi avere diciamo, una certa dimestichezza con la cosa, altrimenti è impossibile. Mentre questo qua è legnoso con tutti i passaggi intermediari, però perlomeno l'idea che tieni ferma una massa su una sfera e quello ti misura la massa che c'è dentro, quello è molto carino. E il fatto di covariantizzarla, cioè che prendi un'espressione che sai cosa è venuto, la covariantizzi, stai seguendo, diciamo, quello è il tuo risultato, quello lo trovo molto
Sì,
carino.
perché è un buon compromesso tra formalismo e fisica, cioè riesce a dare anche a trasmettere la fisica, sono d'accordo.
Quindi era per quello che mi piaceva cercare di infilarla dentro, perché altrimenti rischia di essere ultraformale, ed è il motivo per cui a me piace un sacco, alla fine ci ho provato a farla tutta sta roba del 3D, perché poi devo passare attraverso tutta sta menata qua, no? Che se vuoi allo scopo di definire le simmetrie asintotiche e le cariche, è brillante.
Però insomma questa è una scuola, che la vedano anche esplicitamente
Sì,
non è male, perché poi se la vedevano in letteratura, la gente la menziona, questo spirito secondo me
Però il fatto è che poi dopo, quando finisce tutta questa cosa e arrivi alla teoria del Chern-Simons, cioè veramente non conosci più, perché la teoria del newtoniano Chern-Simons. E sai che cos'è un Poisson bracket, sai che cosa sono i vincoli di prima classe, di seconda classe, sai che una simmetria di Gauge è generata da un vincolo di prima classe e le improper Gauge transformation sono generate da qualcosa che non è più un vincolo di prima classe. Quindi
non ci avevo pensato a questi termini.
e lo vedi da Dio all'interno di questa teoria. Quindi dal punto di vista di fare i conti, non impari, cioè diciamo impari delle tecniche che ti puoi giocare soltanto in questo contesto. Però dal punto di vista di capire Proprio questo adesso purtroppo c'è da soffrire un pochettino per fare tutta la riformulazione, però una volta fatta poi c'hai semplicemente studi cariche in Chansamo e vedi veramente chi era gauge symmetry, appena ci metti in boundary non lo prende più. E l'altra cosa che mi piaceva perché alla fine era l'unica cosa che non vado a sforzare, questa review eterna, stavo scrivendo da 15 anni questo. Adesso finalmente abbiamo una deadline, dovrebbe uscire, però uno dei motivi per cui ci abbiamo impiegato così tanto tempo è che non ci andava fare semplicemente il copia e incolla degli articoli, abbiamo cercato di capire alcune cose e quindi insomma mi sembrava appropriato alcune cose che va bene, influenza di altri.
Un caffè buono.
Can I ask you a question now?
Yeah,
While deriving the Kumar mass integral formula, you defined two form and then showed that the two form was conserved.
yes,
But while showing that the exterior derivative was proportional to the Ricci tensor,
yes.
you used covariant derivative. My question is, in order to define exterior derivative, I really don't need any information about the metric, right? I just need the partial.
Yeah. But I mean, it's just was just a notational stuff. It's a complete overkilling. So in the sense that if you have something like this, well, even something like this, the Christoffel symbol drops out. So it's exactly the same. So essentially, you can define it using any torsion-free connection, and the result is the same.
So the operation was something like this. So in this stead, you use this. And then
It's exactly the same.
yeah, that's true. Okay,
So I just do it for, say, habits or whatever, but then you can use a partial derivative of this so nothing changes because of the antisymmetrization. So even if you use Relativity, in practice, the Christoffel symbol drops out.
and the second question is a little bit about quantum gravity, but you showed the generalized Noether theorem, which is presented in that three-author paper, 1995.
Yeah.
So say that I quantize this thing. Does it still live to a conserved equation in the two theory?
Yes, I don't know. I don't know, fortunately. So it's,
Thank you. That was an explanation.
So I would suggest let's start the Q&A session. In fact, you can ask the question to speakers at any time, but
so we are
the Q&A session is there in such a way that if you ask, your friends might get the benefit for the question also, okay? So, yeah, the atmosphere is really informal and we don't record your questions. So, okay, please, you are encouraged to ask as many questions as possible, and I will pass you microphone, okay? Please.
And you can profit from the fact that the blackboard is still there. So, I mean, I don't know, even if you have questions about, some of you were not familiar with the first order formulation of general relativity, you can even ask about this. So in the sense that it's, yeah, it has been very quick. I understand this, but
Professor, because I didn't know anything about the fiber bundle like that, this formulation. So I just want to wonder question is the omega A and the also the EAB, right? EAB and omega A is the two function we need to solve that. Such as for in general relativity, we need to solve the JAB, right? G mu. We just want to solve the metric.
yeah, so you want to solve the Einstein equation, you mean?
Solve Einstein equation. So in this formulation, we just need to solve the EA mu and the omega mu AB.
Yes.
As a function of space-time.
Well, what do you mean by a function of space-time? In the sense, space-time for you is a manifold or is a Riemannian manifold? You have a metric. In a sense that here you are substituting, so in general, if you take the viewpoint of differential geometry, so you have a differentiable manifold on top of which you put some structure. And typically in GR, people told you, well, the structure that we need is the metric because we want to measure distances, for instance. And we also need the concept of parallel transport, or if you wish, of covariant derivative. And then, well, you can define a lot of different parallel transport because you can define different affine connections. But in GR, people told you, you take Levi-Civita and you're happy. Well, you're happy in the sense that Levi-Civita is the one that has been used by Einstein to build a general relativity. So you have these two structures that you put on top of your differential manifold. So you have a space and you put the structure on top. Here you kind of slightly change the perspective in the sense that the structure that you put on top are these orthonormal bases at each point in space-time, or this object that is called fieldbind, this A mu A, which is a field with a certain structure, and the spin connection, which is another field that you have into the game. So these are the fields that encode completely the dynamics of the gravitational field. And then you can eliminate for the spin connection, and you can just write Einstein equations, which are equations for E mu A, if you wish. And then you can re-express them as being the usual Einstein equations.
Okay, but simplify, basically, we also solve the equation of the coordinates such as x, we have t, x, y, z, such like we have.
Yeah. So you solve equations of motion also in this case. So here the situation that I've shown you is a bit bizarre in the sense that what I'm solving here is an equation. These are the equations of motion. So let me rewrite them together, which is like this. It may be clearer. No, sorry, what the hell I have written? That's this one. So here you have two fields. The fieldbind and the spin connection means two equations of motions, which are these two equations of motion. This equation of motion is the same in any space-time dimension and allow you to eliminate the spin connection. This one is very peculiar of this particular case because it's telling me that the curvature is constant, which is not the case. For instance, in the flat space is even equal to 0. So it's really constant in the sense that you have R equal to 0. But in general, this equation of motion comes in a different form, which I don't, well, I can show you tomorrow. I prefer not to. I write something incorrect, but it's just the fact that it's not the curvature which is equal to 0, but it is a contraction of a curvature with a field bind, which means a particular projection, which means that it's not the full curvature that is equal to 0, but it's just the
Projection.
the Ricci tensor, which is equal to 0.
Okay. And also have another question is, we do the 它现在是 delta EA this equation delta EA equal to the delta epsilon A, yeah.
This one?
Yeah, like this one.
Yeah.
You call that such as Lie derivative. Yeah.
Lie derivative is this one.
Is this one?
This one here.
Yeah, but I don't see any vector with respect to Lie derivative.
No, but the vector is there because
Okay.
if you choose this very particular parameter that contain a vector,
Okay.
then this variation is something that depends on a vector, and it is just the Lie derivative of this form here. In
Okay,
general,
I
this
see.
is not the case. So this object here is just a zero form. It's not
Okay.
a vector. It's a zero form. It's a vector of zero forms in a sense, an element of cotangent space. You can think of it. But if you pick up this very specific parameter, then you realize that there is a diffeomorphism inside.
Okay. Okay. And another, I just a little confused that this form is for the space-time or for the configuration space, just for the space-time, the form. You
What do
mean
you
the
mean?
form? I mean because in the covariant.
No. Let's forget about covariant phase space.
Yeah.
All the mess will come later.
Okay.
So now it's just bread and butter stuff. So
Okay.
just if I talk about a differential form is a differential form in space-time. So I promised you that the idea was to introduce this particular setup that is very specific because it's just three-dimensional, precisely because I didn't want to start with all the machinery of cotangent, of this big complex or whatever. So that will come later. But because I think that here you can appreciate more what are these asymptotic symmetries, and then, I'll introduce also the rest, but the idea is that there are excellent reviews that you can also have a look if you want more details. So here everything is just bread and butter. The only price to pay is that I'm in first order formulation. So then, yes, if it is really the first time, I understand that it could be a bit more complicated, but you can even take a very agnostic things and just say, okay, the guy defined this theory there, and I have the right to do. I give you some field content, I give you an action principle, it is what it is, and then you can take your time after to really check that this is just general relativity. So if you wish, I try to emphasize that the strategy that I will explain to you is something that you can apply to any gauge theory, not necessarily to gravity. It's gravity that requires this kind of techniques because more ad hoc techniques do not work, but you can just take, okay, we define a crazy gauge theory, which is a nice toy model to try to understand what is an asymptotic symmetry. Okay. And then a posteriori, you can also check that this is gravity in 3 dimensions.
Okay. Oh, thank you.
There is...
Always about this formalism, EA
Yes.
in general. Is it E mu A V mu? Because the base
yes.
of TP.
Yeah. So maybe I went too fast when I introduced it. So where can I do it? Let's go here so that I can keep all the formula that we have there. So essentially here what I'm introduced a one form, EA, and being a one form, I can write it in this particular way. And the same is true for the spin connection.
Okay, now I understand.
Okay, and
yeah.
so this And then you
So
can
it's-
even do things that
it's-
are more, say, intrinsic, and you can also express this one in a orthonormal basis. Because here, clearly, I've chosen a basis just to make things clearer for people that are maybe not familiar with orthonormal basis. But of course, I can also express these objects in another basis. So that is just a matter of making a choice.
Yeah, okay, thank you.
And like this, and this is really when I write something like EA wedge EB, what I mean is just, if you wish, something like is E mu, well, probably with a normalization. Okay, so that is, it's really differential form calculus. Yeah, by the way, so that's maybe I should have asked. That's I really gave for granted. So are you familiar with differential form calculus? Because that's, well, here is the easy version of it. Then it will become even a bit more abstract as someone anticipated when I will move to covariant phase space techniques. But it's always differential form calculus, essentially. And once again, yeah, so, yeah, you can even take this theory as a crazy theory that has been defined for the sake of making an example, but I think that the important things to appreciate is that it's not so crazy, because apart from the fact that there are some things that are much easier to do here. So in some books, you, for instance, you solve for the Schwarzschild solution in this form. It's much easier than just computing all the Christoffel symbol. Probably all of you did. You should do once in your life, but if you do it there, it's easier. In a sense, you do less computations. But apart from the these aspects that is nice, as soon as you are familiar with it, is really necessary, because if you want to couple fermions to gravity, you have to pass through it. Because of this reason, that you really want to see Lorentz symmetry realized locally, because otherwise, locally, you don't know how to define a spinor field. If you want to define a vector, it's fine. If you want to define a scalar, it's fine. But if you want to define what is an electron, well, maybe it's not something that we typically do, because you don't have spinor fields that are really defined everywhere or in gravitational context. But formally, if you want to define what is a spinor in a gravitational context, you have to pass through this formulation. So in this sense, it's something that is important. And then, so the other lecture is about supersymmetry. So you don't need it, but as soon as you move to supergravity, well, that is your theory. No way to do supergravity without the first order formulation. Then there are some other formulations in which a spin connection is not in it's not an independent field that you can do, so you can do all type of variety of things, but you need an orthonormal basis, you need local Lorentz transformation locally. So in this sense, it's something that it could be also a motivation or an occasion to have a look at this kind of theories, because they are very useful, and it's a good complement of your knowledge about GR, essentially. And well, it depends at the level of formality that you like to see. If you really want to see this viewpoint of orthonormal phrasing, a good reference is just the book by Nakahara, which is a big book in which there is everything, but in this particular case it's not so bad. So it just, I don't know, I think it's 10, 15 pages in the middle of a big book, and it's not crazily mathematical with respect maybe to other parts. So it's usually a good reference for this. Otherwise, the other reference for this typically are books about supergravity. Van Proyen and Friedman is working with this formalism and so on, and so, because there they are forced to do. So it's
I got a bit lost when we introduced A up left, meaning
yes.
that, I mean, we wrote that formula, but P and L are just the objects that like have that commutation relations, or are something else that we introduced and I...
No, are the objects with these commutation relations. So the idea is that is like a Young-Mills connection. In the case of a Young-Mills connection, what do you do? So it's here. for Young-Mills, you introduce an object. Well, let's do all the chain, so it's just this one, a priori, but then you can write it in this way. Okay, so it is a vector, or a one form, if you wish, and you expand it in the generators of a Lie algebra. Here I'm doing exactly the same. So it's just that I've chosen a specific Lie algebra, and my specific Lie algebra, if you wish, the same expression that I've written there. So let's leave the 1 over g, which I set g equal to 1, that it's to simplify life. So essentially what I'm written there is, I call it P, A, that I call L. So you see, it's precisely like a Young-Mills connection for a specific algebra. And the specific algebra, depending on the sign of a cosmological constant, is Poincaré, anti-de Sitter or de Sitter. And that's up to this trick you can also do in the case of gravity in 4D. So you can write the torsion and the curvature starting from Lie algebra valued connection, but the problem is what is the action? Because this guy is like a Young-Mills field, but look at the action, it's not at all a Young-Mills action. And in particular, the field equations of this action are pretty trivial because the field equations are just, let's say I'm anticipating something that will come tomorrow. The curvature is equal to 0. And again, seems extremely boring if you look from this perspective, but this is just the counterpart of this one. You already know this information. It's the translation of this information there. So that the theory locally is super boring, we know, so there was a disclaimer at the beginning, but globally, these theories here are not. So one thing is what is the structure of the field, one thing is the action. So even in the case of general relativity in 4 dimensions, so you can have an analog of this action here, which is taking exactly the same form. Just for the sake of completeness, I can even A, B, C, D. It's just this in 4 dimensions, but having or not having this term here makes a huge difference because, well, it changes drastically the equations of motion. And you see why, because if I take a variation with respect to the spin connection, then I will eat one guy more here. It's not just the curvature, and then it changes completely the structure of the equations of motion, but it also changes the structure of the action. In particular, I'm not able anymore to write this gauge symmetry action. So the equations of motion are I can write them in terms of curvature even in higher dimension, but the action not. And one reason is that in higher dimension I can do the same. So I can produce a Young-Mills connection, where here I have a translation generators, and here I have a rotation generators. Is enough to do this. And I can write the curvature and the torsion as Young-Mills connection for this object here, but this action here is invariant. So we know that Young-Mills also has some gauge transformations. And these gauge transformation, I have them also here. And in the case of gravity, this will lead to local translations and local Lorentz, but it's impossible to write an action which is invariant under local translations, as it should, because essentially local Lorentz locally, I know that it's like flat space-time, but I cannot do translations because the translation symmetry becomes a diffeomorphic symmetry because my space is curved. So I cannot move from one place to another. While here, the space, yes, is curved, but is of constant curvature. So it's like moving in the vacuum, in a sense, even, again, only locally, but...
Okay, I would like to ask something about that despite in 3 dimensions, when there is a cosmological constant, curvature is somehow constant at any point.
Yes.
But you okay, one might have black hole solutions despite
Yes.
this fact by let's say making a orbifold, then some identification
it's
of
kind of
points,
orbifold
kind of
procedure,
orbifold, yeah,
yes, yes.
identification of points in three-dimensional anti-de Sitter. So is that BTZ black hole?
It's the BTZ black hole,
Okay, okay.
exactly.
And where is the let's say the process, the exact process in such a way the curvature gets infinite if it gets infinite?
No, it doesn't get infinite. No, that's is the singularity of the BTZ black hole. I was mentioning in passing by. It was I was commenting about the BTZ black hole because there are black hole solutions only if the cosmological constant is positive. Somehow, in the limit in which the cosmological constant goes to zero, what happens roughly is that you have the BTZ black hole is like a curved black hole. It has an outer and inner horizon. And somehow what you are exploring in this particular case is just that the horizon is pushed to infinity. So you are kind of pushing the horizons to infinity, and you don't have black holes if space-time is flat. But in the case of BTZ black hole, there is an horizon and there is a singularity, but singularity is a chronological singularity. So you can pass through it, but you will have closed time-like curves. So then this means that people typically, it's a toy model anyway, no? And in this toy model, you consider this chronological singularity as a true singularity and remove it from space-time. So you decide that space-time ends there. If you chop out a piece of space-time, you are making a space-time which is not geodesically complete. In practice, it's the same thing as having a singularity, because you eat something in a finite amount of time, and this you eat the part of space that you have chopped out. A priori, you can cross it, but then you will encounter closed time-like curves.
Okay.
And the reason is just that, okay, without entering in the details is a bit difficult, but the fact is that how you can make identification by points, you need symmetries. Once again. So the only thing that you can do it is that you take a Killing vector, you follow it, and you make identification of points along the orbits of a Killing vector. But here we have plenty of them, so we have 6 of them, because you have a Killing vector of anti-de Sitter. And you just follow the orbits of Killing vectors, and you say that along the orbits you identify some points along these. But since you identify points, well, you know that space-like vectors become time-like when you cross the horizon, which is going to happen. And then if you identify points around space time-like curves, typically it's not a good thing because they become circles. And this is your chronological singularity, because your identification of points, you have a line that a priori is open line. You decide that after 2 pi, you close it, it becomes a circle, and you have closed time-like curves. But so for that, if you are interested in this, the best reference remain the paper, not the BTZ one, but the BTZ-H one. So there are 2 papers. BTZ means Bagnados, Teitelbaum, and Zanelli. The first paper, we just solved the equations of motion. We solved the equation of motion, and we found an horizon. And the story seems that the referee refused to accept the paper, but eventually we managed to convince him because he said it's not possible, it doesn't exist. But eventually it was correct, so they do have an horizon. And then there is a paper with also Marc Henault, a year later or whatever, and there is all the causal structure of a BTZ black hole, which is explained in great detail in full glory. I would say that, well, I haven't read them, but I saw that also in the lecture notes that I was citing, the one Compare Fiorucci, they do a review of these, but essentially it's probably based on that paper that remained the best reference if you want to understand the BTZ black hole as a Lorentzian solution.
Not Euclidean.
Because then there is also all the business of Euclidean continuation, the entropy, and so on and so forth. So three-dimensional gravity is very rich, but the goal of this lecture is not to do lecture on 3D gravity, so I'm just using it as a tool to explain asymptotic symmetries. If you like 3D, you can have a lot of fun with it, because there are a lot of interesting things that you can do. In particular, it's the best place where to study black holes, because everything is easier and nice, and you have a black hole that is more tractable than care, and you can compute its entropy and a lot of things. So there are thousands of papers about nothing. Because it's so.
Thank you.
So Chern-Simons theory is a topological field theory.
Yes.
So does that mean the 3D gravity is a topological theory?
Yes. Well, what do you mean by topological theory?
Yes,
First of all, so
correlation functions shouldn't depend on the metric. I mean, observables don't depend on
well,
the
because topological theory sometimes means two things. So one thing is that there are no degrees of freedom.
Okay.
And this is the case. So my Weil tensor is equal to 0. So here I have no propagating degrees of freedom. Or if you wish, if you linearize the equations of motion, there are no wave solutions. So in this sense, it is topological because there are no propagating degrees of freedom. And it is topological also in the other sense, because in order to define the action, I didn't need a metric. So the metric is a sort of emergent concept that I can do. I can define a metric. Well, here, but I don't need it. In order to define the action, I just have to integrate over M, where M is a differential manifold, and that's it. I don't need the metric, because, which is something a bit peculiar. For instance, not the case in Young-Mills. In Young-Mills, you can write the action in terms of differential forms as f wedge star f, but there is a star in between. So you have you do a notch duality, and so you need the metric. While in this particular case, I don't need any metric. So it's topological in both sense.
Doesn't the field line appear in A? But the field line isn't the
yes, the field line appear in A, but is a one form.
Okay.
For instance, one thing that you can do, and some people that looked at quantization did, although it's a bit tricky. So here in general relativity, you work with a non-degenerate metric. But here I don't have to, a priori. So I can even play with a fieldbine, which give me a degenerate metric. And from the viewpoint of the Chern-Simons theory is allowed. Now it's up to you. Do you want to include or not to include this kind of solutions? And there are all types of craziness. So people said, well, if you don't include them, you cannot quantize. So it's, I mean, it's true that there are thousands of papers on the topic. But what I'll try to do here is to be as conservative as possible. So for instance, some of the things that I will do for asymptotic symmetries, there are people are much easier if you go in a gauge in which the fieldbine is degenerate. So you just use your gauge symmetry, this one, to go in a gauge, which is a very convenient one, and in this gauge, the fieldbine is manifestly degenerate. So it's clear that the metric will be degenerate, but this doesn't affect the discussion of the asymptotic symmetries. That's I will try to avoid as much as possible. So to be also because the goal is, again, to learn something about more general cases. But a priori, you can even do more crazy stuff because the metric is just a derived concept. And yeah, and for instance, in this kind of theories, it's a bit simpler to include topology changes or this kind of phenomena that are a bit more artificial, maybe in second-order formulations. But I must say that this theory seems to be so simple. But for instance, there is no, yeah, so there have been several attempts to quantize it, but I would say that there is no, so to be optimist, there is no agreement that people manage to do, but in even the quantization of this theory, there is a, yeah, there is a paper by Witten of 84, 86. It's a nice introduction about 3D gravity because it tells you, he has this style, Witten, of writing that is very entertaining in a sense. He likes to explain things, and it says from some perspective, this theory is obviously not renormalizable, and from some perspective, this theory is obviously trivial. So either one or the other. And then he tries to find his way to quantize, but it didn't work. So we don't know if we can quantize even this theory. So clearly, people worked a lot on this particular model. well, as a toy model to learn things about black holes, asymptotic symmetries, and so on and so forth. But because the hope was that if we are not even able to quantize that, how can we quantize gravity in 4D? But the problem is that we are still there, but we haven't quantized it. So.
So if there are no other questions, maybe it's time to move to the first lecture.